Hi everyone, welcome back to another video. In this session we're going to be looking at nodal voltage analysis. In the previous video we looked at method of branch current, and for this example we had our answers which are listed here. We had a set of rules and laws that we followed, but in this example we're going to be looking at the nodal voltage analysis. And firstly what I want to do is discuss the 5 steps like I did in the previous video for this example, using Kirchhoff's voltage laws. So firstly, what we're going to do like previously, we're going to mark each power source and resistor with a positive and negative sign. Secondly, we're going to indicate the assumed current. Thirdly, we're going to identify the principal nodes. So these are going to be points where we have where we have 3 or more components. And for these points on these nodes, we're going to write down the nodal equations for currents. And that's going to be using Kirchhoff's current law as an example right up here. And lastly, once we get these equations, we're going to express the currents using current equals voltage divided by R, so V over R. So finally we're going to use Ohm's law to calculate the currents across each resistor. So what I want to do firstly is look at number 1, mark each power source and resistor with a positive and negative sign. So remember, as discussed in the last video, the negative or the short terminal of the battery is the negative. That means the long line or the long terminal is positive. So we're going to do that with the same battery on the other side. So as this is the negative terminal, what we say is that the electrons, which are negatively charged, flow from negative to positive. Therefore, if you imagine the current's going to flow in a clockwise direction in this loop, and likewise this is the negative sign, that's the positive, so negative to positive is counterclockwise. Again, this was exactly the same as the method of branch currents. With this we can say from the loop on the left hand side, but as the current leaves this negative terminal, it's going to travel up, get to this corner, meet the first resistor here, and that first point is going to be negative. As the electrons first meet that resistor, that's going to be negative. And then this side will be positive. And likewise with this 6 ohm resistor, the current's going to go up to the left. That means this sign is going to be negative, this is going to be positive. And now at this point we've got 2 sets of currents. We've got one current going from this battery source up to the right, and we've got another current going from this battery source up to the left, and that's going to meet at this node. So that means as the current goes through, there's only one way, which is going to be downwards. So there's 3 currents. We're going to label this I1, I2 and I3, and using our key we can say that when the currents enter the flow, they must equal the current exiting the flow. So we've got our power source and resistors labelled up with positive and negative signs. We've looked at the current directions, that's clockwise and that's counterclockwise for both loops. 3, we're going to identify the principal nodes, which are points with 3 or more components. So that's going to be this node here. Can you see you've got a resistor on the left, resistor to the right, and the resistor down below. So that has 3 connection points. And what we're going to do is, just for ease of sake, we're going to label these points A, B, C, D. That's your ground. So that's your ground there. We'll label that point E though, and F. And as mentioned before, at point B, which is the principal node, we can say that I3 is equal to the current inflowing, which is I1 plus I2. Exactly like this key. Remember, for continuity and looking at Kirchhoff's law, the current flowing into a node must equal the current exiting the node. So, using I3 equals I1 plus I2, let's begin writing equations for each resistor. Now remember, voltage equals current times resistance. That means if we replace as we're going to be writing these equations as V over R, we need to say that current equals V over R. Now, we're going to use this principle of I equals voltage over resistance, and we're going to use that for each resistor. So let's start with the left-hand loop. A, B, E, F, A. As the current starts at the power source, which is the battery, it's going to go up to point A and right across to resistor 1, which is the 24 ohms. So let's call that resistor 1. We can say that's resistor 2, the 6 ohm, and that's going to be resistor 3. So I1, which is the current flowing in this loop, is going to be the voltage divided by the current. So the voltage we always take from the positive sign minus the negative sign. So the positive sign is voltage at B. So can you see at this resistance, the positive side here has the voltage of B, and that means negative is going to be the voltage at A. So we're going to be looking at those points. If we say I1 plus I2 is equal to I3, therefore we can replace I1 with positive, which is VB, minus VA, which is the negative side, over the resistance, which is 24. Now we can do the same with I2. I2, the positive side is VB, the negative side is VC, and that's going to be over the resistance, so V over R, which is 6, and that should equal I3. Now our I3 is going down. This side, as I3 is going down, that means this side is negative, or the resistance, this side is positive. So as we're doing positive minus negative, positive is the ground, which is the next nearest node, which is VG, so that's the ground, minus VB, which in this case here is the negative, over resistance, which is 12. So what we're going to do from this side is going to plug in the numbers that we know. So we know VA, VC and VB. So what is VA? VA is the current coming out of the power source. As this is the power source, the battery, we've got 168 volts coming straight out. There's no component in between. There's not being used by anything. So we've got the full voltage at A. And as it leaves the negative terminal, that is negative. Now if we look at C, again, there's no components as the electrons leave the battery, so it has the full voltage at VC, which is negative 42 as it leaves the negative terminal first. We're going to use these signs as it's really important to be consistent through our equations to get the right answer at the end. So VB, we don't know what the voltage is because we've got resistance in between, so we don't know what value of voltage is being consumed. So that's VB minus VA, which is minus 168 all over 24, and then VB again, which we don't know, minus VC, which we just said is 42, negative 42 over 6, equals to VG, ground, is always 0, always also known as the earthing point, which is 0, minus VB, which we don't know, all over 12. Now what we want to do is to eliminate these denominators and just to get VB and these numerical answers by itself. So what we're going to do is just get rid of these denominators by multiplying through the largest number, which is multiplied by 24, and that's going to be through everything. So we got VB minus, and a minus is a plus, so that's a plus 168. Now multiplying by 24, that means this bracket, or VB plus 42, will be times by 4, so that's plus 4 lots of VB plus 42 is equal to 2 lots of negative VB, as that's been multiplied by 24. So if we collate the like terms, what do we get? We've got VB plus 4VB, and that's going to be positive 5VB. We've got 168 plus 4 times 42, so that in itself is another 168. So 168 plus 168 is 336 equals to negative 2 VB. So if we get VB isolated and we divide through, we get VB as negative 48 volts. What we can do is get this new VB and then plug it in to the voltage drops across R1 and R2. Remember, this I1 is the voltage drop across resistor 1, this is the voltage drop across resistor 2, and likewise this is the voltage drop across resistor 3. So therefore we can say that voltage across R1 is equal, just like what we said here, is VB minus VA. So VB, which just worked out, is minus 48 minus VA, which is negative 168, which is plus 168. So we can say VR1 is equal to a positive 120 volts, just like what we found out in the method of branch currents on the right hand side. So that's a tick mark for us. Let's do the same thing. Let's just work on the right hand side so we can see everything. Let's work out VR2, so the voltage drop across resistor 2, and again what we found out from my equation is VB minus VC. So that's going to equal minus 48 minus VC, which is minus 42, so that's going to be a plus 42 is equal to minus 6 volts. Again, from our method of branch currents, that's exactly what we saw. And what we'll notice is, once we come to work out the current, that should also be negative 1 amp. And that's going to be because we've assumed the wrong current direction. But that's alright, because as we've been consistent through our calculations, we should get the right answers as we work through it. Now let's work out the voltage drop across R3. Again, we worked out here is VG minus VB. VG is 0 minus VB, which is positive 48. So that's exactly what we found here in the method of branch currents. Therefore, what we can say is the current across resistor 1 is just going to be voltage across resistor 1 all over the total resistance of R1. So VR1 is 120 divided by the resistance is 24, that equals 5 amps. Exactly what we saw in the method of branch currents, so that's a tick. And therefore we can say IR2 is VR2 divided by resistor 2, which is minus 6 volts divided by 6 ohms, that's minus 1 amp. Exactly what we saw in the method of branch currents. And finally we've got IR3 is equal to VR3 minus R3, which is 48 divided by 12, which is 4 amps. And as a check, remember what we said, I3 is equal to I1 plus I2, so therefore I1 plus I2, which is 5 amps plus negative 1 equals 4 amps, and that's exactly what we got as I3, so that's a check. So hopefully that's made sense. If you've enjoyed the video, please leave a like, please consider subscribing, and I'll see you in the next video. Take care.